Hey Wade, now let's talk about conditional probability. And specifically, we're going to talk about how to solve conditional probability problems with tables. So, first of all, let's talk about what conditional probability is. Like, what does that even mean? And the definition, it says the conditional probability of an event B is the probability that the event will occur given that A has already occurred. And we talked about how we can write this as the probability of B given, this line means given, A. And technically, the definition of conditional probability, if I wanted to go ahead and write this kind of as a formula, is that the probability of B given A is equal to the probability of A and B over the probability of A. This will come up sometimes, but generally in this class, we're going to be looking at either Bayes' rule or solving these probability questions with different rules. So it does say this expression is only valid when the P of A is not equal to 0 because we can't have 0 in the denominator or the world will explode. And in the case where A and B are independent, the conditional probability of B given A is just the probability of B. So we've seen this with the multiplication rule. So let's go ahead and dive into our first example. One way to go ahead about solving these conditional probability problems is to use tables. And the first one is actually about courts and juries. So it says, suppose jurors make the right decisions about guilt and innocence 90% of the time, and the 80% of all defendants are truly guilty. So wait, do you know about this? Do you know about jurors and being guilty and innocent?
I know about them, but it's scary to kind of think about guilty people or innocent people being declared guilty by a court.
Exactly. So this did say, suppose jurors make the right decision. So what would be the right decision for someone who's innocent?
So they would be not guilty of the crime.
Right. So if they're not guilty, they should be acquitted.
Yes.
Right. And then a guilty person, what about them?
They would be convicted.
They would be convicted. So I'm just going ahead and putting these little stars in the cells where those are the right decisions. So we know that happens 90% of the time, but I can't really do anything with this table until I fill in my total column. So we always want to fill in the total column first, or if they give me the total row, that's totally fine. So let's see, it says 80% of all defendants are truly guilty. So of this, it looks like it's for 100 people. So 80% of 100 is just 80. So there are 80 guilty people. And then what does that mean about innocent people?
So you said that the column has to add up all the same, or add up to the total.
Yep.
So 100 minus 80 is 20.
Exactly. So in these tables, the rows and columns have to sum. And I guess I should say too, why are we filling out this table? The reason we're doing that is because I want to answer these questions about conditional probability. What's the probability that a person is convicted given that they are innocent? And once I have the table, I can just look at the table and I'll see my answer. Otherwise, right now, this would be a little tricky to figure out without the table, or either we could use a formula as well. So I'm going to keep filling this out and then I'll answer the questions. We also know I used my first piece of information, 80% of all defendants are truly guilty. And then 90% of the time, the right decisions are made. So we have 20 innocent people, 90% of those 20 people will be correctly acquitted. So Wade has Python pulled up. I'm going to just ask you for the numbers if that's okay.
Sure.
90% of 20.
So that's just 18.
18, that was, probably didn't need a calculator for that one. That was my fault. And then, so if 18 of the 20 innocent people are acquitted, 2 of them would be convicted, which you said was kind of scary.
Yeah, innocent person going to jail.
Yeah, for something they didn't do. Yikes. And then for the 80 guilty people, 90% of those 80 guilty people will correctly be convicted, which is
72 of them.
72 of them. And then the rest, which would be 8 of them, would be acquitted. So that would be guilty. Ooh, that's bad too.
Yeah, guilty person walking free.
Oh gosh, yeah. Depending on the crime, that could be worse. Yeah, based on that. So then I am almost done with my table. I'm going to go ahead and sum these columns. So 18 plus 8 is 26 people were acquitted, and then 74 people were convicted. So now that I have this table, this question should be a lot easier. It says, what's the probability that a person is convicted? I'm going to use my probability notation, given that they are innocent. So this is that, we don't like that, right? We're saying, what's the probability that they're convicted given they're one of these 20 innocent people? So I know that the denominator is going to be 20 because it says given they're innocent, and we know there are 20 innocent people. The probability that they're going to be convicted, only 2 of them are going to be convicted. So 2 out of 20 is just 10%. So that's low, but kind of scary that it's not 0. So kind of just like we talked about, medical tests aren't always 100% accurate. Neither is our court system. And then the last question says, what's the probability that a person is innocent? Probability that they're innocent given that they are convicted. So this sounds very similar to the previous question, but we're going to see here that the probability of A given B is not always equal to the probability of B given A. Actually, it's usually not. And in this case specifically, we know that the person is convicted. It says given that they're convicted. So there are 74 total convicted people, and only 2 of them are innocent. So I'm going to have Wade pull up that percentage.
2 over 74 is 0.027.
0.027%.
That's going to be a decimal, so it's going to be 2.7%.
Got it. 2.7%. Yes, Python does give us a decimal between 0 and 1. If I want to convert that to a percentage between 0 and 100, I'm just going to move the decimal. So we can definitely see here that if they're convicted, given that they're convicted, there's only a 2.7% chance that they're innocent. So I want to do one more example with a conditional probability table just so we can see this in another context. So we have medical tests, and again, like I said, medical tests aren't always accurate. So conditional probability makes sense. It says, let's say that 50% of women, this is about a pregnancy test, who take pregnancy tests are actually pregnant. And our overall total is 10,000 people. They want us to fill in the table for 10,000 people. So 50% of women who take the tests are actually pregnant. I can actually go ahead. That is my first row total. So I can say 50% of 10,000 and fill that in. So 5,000 people are pregnant, 5,000 are not, at least for this particular test. And then it says, suppose there's a new pregnancy test that we know the following information. 92% of women who are pregnant will correctly get a positive result. So of these 5,000 women who are pregnant, 92% of them will get a positive result.
So I did some math. If you wanted the whole number.
Let's round to the nearest whole number. Yes.
Yeah, 4,600.
4,600. And then that means that 400 of them are going to get a negative result. So that's for pregnant, but test negative. Maybe it was too early to detect. That happens sometimes. So that's the first row. And then if I keep reading the problem, it also says 6% of women who are not pregnant will also get a positive result. So 0.06 times there are also 5,000 people who are not pregnant.
That's 300 people.
So 300 people will get a false positive. And then I have 4,700 people who will correctly test negative. So again, in this table, it just happens to be the same, that if you're pregnant, you want to test positive. If you're not pregnant, you want to test negative. Those cells that are the correct answers happen to be in the same spot, but that doesn't have to be the case. And then I have 4,900 for test positive total. And I also have 5,100 for negative total tests. And I should have looked at the question, I guess, before I filled out the table. But now that I have my table filled out, I can answer any of these questions. So the first one says a woman gets a positive test result. Okay, so we know they're in this column. What's the chance she's actually pregnant? So my denominator is going to be 4,900 because we know they got a positive result. And the chance that she's actually pregnant is 4,600 out of 1,900. So I could write this in probability notation. I could say, what's the probability that she is actually pregnant? Given, our given is that she got a positive result. Oops. And Wade, what do we get for that probability?
4,600 divided by 4,900
Yes.
is 0.9388.
93.88%. So if she gets a positive result, what's the chance she's actually pregnant? 93.88%. Next, it says, given that a woman is not pregnant, so we know they are one of these 5,000 people who are not pregnant, what's the chance she'll get a negative result? And that is 4,700. If I look in the row for not pregnant, 5,000 total, 4,700 will test negative.
And that's 94%.
94%. And both of these are asking about, okay, they're saying she's pregnant. What's the chance the result is positive? And then not pregnant and negative. They're both kind of the right things that should happen. And if I wanted to write this in probability notation, I could say, what's the probability that a woman gets a negative result given that she is not pregnant? Next, it says, what's the probability of getting a false positive? So Wade, what exactly does false positive mean again?
So false positive is going to be they get a positive result, but they're not actually pregnant?
Yes, exactly. So if we look at this table, what's the probability that we get a false positive? Let's think about what that means in terms of probability notation and conditional probability. So what should I write for a false positive?
Well, so this is what a false positive is. They are receiving a positive result. So they get the positive result given that they are not actually pregnant.
Given that they are not pregnant. And so we know that they're not pregnant, so they're one of the 5,000 people who are not pregnant. And then there's only 300 of them that will get a positive result. So the false positive rate is going to be what?
6%.
6%. And that actually makes sense looking at the previous question. If I look at how I wrote that, I said, what's the probability they get a negative result given that they're not pregnant? And the only other option is a positive result. So this 94 plus 6 should give me 100%. So the very last question on this puzzle says, in general, is the probability of A given B always the same as the probability of B given A? And we said no, right? We've definitely seen that before. The probability of A given B is not always equal to the probability of B given A. But it can be depending on the problem. But here, if I looked at the probability that, let's just say I looked at the probability that a woman is pregnant given that they tested positive, and the probability that they tested positive given they're pregnant, those would be two different numbers. So I think that is it for conditional probability. Have fun nerding out.